Hello, everyone. My name is Hassan Ghasemzadeh. I'm an associate professor of biomedical informatics in the College of Health Solutions at Arizona State University. Today, I'm going to talk about some of the technologies that we have been developing for glucose control. So my lab is called Embedded Machine Intelligence Lab. We conduct research at the intersection of wearable technologies and AI. Some of the biomarkers that we have studied in the past focus on physical activity, human behavior, diet, medication, glucose, stress and gait, mobility, human balance. And some of the application domains include diabetes, cardiovascular disease, heart failure, Parkinson's disease, Alzheimer's disease, and alcohol use disorder. So the focus of this talk will be on glucose control, and we know that there is a strong interplay between glucose and various chronic conditions. So some facts about chronic conditions. 2/3 of deaths are due to various chronic conditions such as diabetes and cancer. 1/3 of American adults are projected to have type 2 diabetes by 2050. So we spend $4.3 trillion on healthcare in the US. And a majority of this is attributed to chronic conditions. And this is despite the fact that 75% of chronic conditions can be actually prevented or delayed by maintaining healthy lifestyle. And glucose control has a significant, basically, impact on maintaining this goal. So glucose control refers to maintaining a normal glucose level. So as you see on the graph on the left, the normal range might vary, in fact, depending on the context. For example, at fasting, usually normal range means 70 milligram per deciliter to 100. So that's considered normal, but after meal glucose level is supposed to not exceed 160 milligram per deciliter. Otherwise, it's going to be hyperglycemia, as you see in this graph on the right. So glucose control can help individuals lose weight, optimize their mental health, suppress food craving, can improve sleep, and prevent diabetes, of course. And poor glucose control will increase risk of cardiovascular disease, kidney disease, stroke, cancer, and other complications. The question for us was, what are the type of technologies that we can develop in order to help with glucose control? So the first thing that we focused on was designing technologies that can help with predicting hyperglycemia, this spike after eating a meal. So objective was to design a machine learning model that will gather and capture basically data about meals, about glucose through continuous glucose monitors or CGM devices. If a patient is on insulin, also information about the amount and timing of insulin. And this multimodal data is fed into a machine learning model that will predict postprandial hyperglycemia, whether or not the person will have hyperglycemia by eating this food. And their objective was basically to make sure that this model is interpretable in the sense that it can provide actionable information in order to prevent hyperglycemia. So you can look at the use case as, the patient is about to eat certain food and they can enter information about what they're about to eat, and the algorithm will prompt them whether they will experience hyperglycemia or not and how to prevent it. So with that in mind, the first thing that we focused on was constructing a decision tree model. And the main reason is that decision tree models are the kind of machine learning models that are inherently interpretable. So if you look at this example of decision tree, you can see that the most informative feature from the data was for this particular patient was, the amount of bolus insulin amount, and that feature basically. So we put a threshold on that. If the amount of bolus insulin is above certain threshold, in this case 0.27, then the second feature that is important is carb amount, and if the carb amount is above 40 grams, then the algorithm suggests it's hyperglycemia, otherwise there's no hyperglycemia. And you can see on the left, basically, branch what happens in terms of how the algorithm makes decisions. So this would kind of naturally leads us to providing guidelines about how the algorithm makes decision, but how potentially the patient can prevent hyperglycemia. So we trained a model using data from 5 patients with type 1 and type 2 diabetes. Information about these patients are shown in the table. You see that patients were monitored in a feeding study between 11 days and 23 days. With a total of 167 meals. And so continuous glucose monitor device was used for capturing glucose. They reported, basically we also knew the amount. So this was a publicly available data set. And with this small kind of data set, we were able to train models per individual, per patient, and also a more kind of general model for the population. These are some of the results based on leave one meal out and leave one subject out analysis, mainly because we wanted to assess the generalizability of the model. As you see on this column decision tree on the right, so leave one subject out analysis shows that we get 68.8% accuracy and about 81% F1 score in terms of how accurate the algorithm is, the decision tree. We also did analysis with support vector machine, SVM. You see the result here. But overall, as you see, so the accuracy about 80% in terms of F1 score. The table at the bottom shows the so we did basically some feature selection as well. Here in this table, you see the top 2 features that are most predictive of hyperglycemia for individual patients and also for the generalized model. So as you see, in most of these models, carb amount or carb composition is one of the most important features, which is consistent with what we know from the literature, that carb contributes most to hyperglycemia. So with this, we also noticed the moderate amount of accuracy that we achieved with this, but this was promising as a first step. So next step for us was to design a deep learning model at the hope that we can achieve higher amount of accuracy and do a little better in terms of prediction horizon. So in here we looked at another data set that includes information about carb, for example. This is type 1 diabetes patients, Ohio data set. That's what is referred to. Carb amount, exercise, sleep, and work, basically these different types of activities that patients report through a smartphone app, a wristband that is used to measure heart rate, skin temperature, galvanic skin response, accelerometer, and also information about time of the day. And CGM, which captures continuous glucose every 5 minutes, and also these patients were on insulin pumps, so basal and bolus insulin amount were also known. So as you see on the left, so we try to design a multitask learning model that will actually predict the glucose level in the next 5 minutes, next 30 minutes, and next hour. And on the right, you see details of the model, which is a stacked CNN LSTM architecture that looks at the past 3 hours of data and try to predict the next 5 minutes, 30 minutes, and 1 hour glucose. So with this, an Ohio data set. We trained a model for this population. This data set includes 12 participants. We excluded 2 of them because they had incomplete data for the type of analysis that we want to do here. As you see in this table in the right, the amount of error in terms of mean absolute error to predict the glucose level varies from 8.2 milligram per deciliter to 16.5, depending on the prediction horizon. The longer the prediction horizon, the higher the amount of error is. And we also looked at these amounts and tried to see, okay, whether or not the algorithm actually is inferring hyperglycemic events or not. And the table at the bottom shows the accuracy in terms of predicting hyperglycemia, which we achieved 89.3% accuracy in terms of predicting hyperglycemia. So this was good, a significant improvement from the previous model, but the limitation here is that this is a black box model like any other deep learning model. So it doesn't provide any interpretation in terms of why the model made the decision and how the patient can actually prevent hyperglycemia. So next step for us was to see how we can design algorithms that actually help with preventing hyperglycemia. For that one, our focus was on counterfactual explanations. So what is counterfactual explanation? Let's look at it through a toy example, and that's loan approval system. So in a loan approval system, usually there is data about an individual, about their income, their age, their occupation, and other factors, and an AI model can make recommendations, approve or decline this loan request, right? So as you see in this graph, so in a simplified version, so the toy example, there are 2 parameters, income and age. And on the left side of this decision boundary, the curve that you see is basically decline, on the right is approve. So assume that the person's income is 32K and the age is 39. That's the factual example. And in this case, the loan request is declined according to the AI model. So counterfactual examples are examples that change these features in order to flip the class label, meaning that now move the data point to the right side of the curve, therefore the loan gets approved. So that way you can provide feedback to the individual how they could have actually got approved for the loan. So there are 3 examples of counterfactual explanations here. Number 1 is the one when you move across income coordinate, and so the income goes to 40K, the age remains the same, and that could be one example. Another is counterfactual number 2. As you see, basically you move along both axes, and income goes up to 36 and the age 44, which means the person needs to improve their income, but also wait 5 years for loan to get approved. And in extreme case, if you move only along the age axis, the person age needs to be 140, which is kind of, it's a hypothetical case, right? It's not realistic. So as you see, counterfactual are not necessarily real examples, and it's important for us to develop them in a way that they are actually realistic and can be implemented in practice. So borrowing some of ideas from this domain, now how can we design counterfactual explanations in order to prevent hyperglycemia? So what it really means is that assume we know the decision boundary, right? These on the left graph you see green kind of samples. These are normal kind of glycemic events, and the red ones are abnormal, for example, hyperglycemia. So assume the dashed lines are is the decision boundary between these 2 groups or regions or classes. So the first thing for us was actually to construct this decision boundary, because that doesn't exist in the data set. For that one, what we did, we extracted or generated adversarial samples along the decision boundary, and that would allow us to approximate the decision hyperplane, as you see in the graph in the middle. And then once we construct a decision boundary, we can remove the training data that we have. On the right, you see that now we have the decision boundary. So if the algorithm predicts that this person will experience hyperglycemia, as you see in this graph on the right, then we can move along different axes. And the XY axis here, it could be different behavioral factors such as macronutrients, fiber, carb. It could be physical activity, exercise, and things of that sort, or medication, specifically insulin amount and timing. So these are various factors that we can modify. But what is important in this case, first, we need to make minimal amount of change in a person's behavior, and that's how we can actually prevent the event. Radical changes won't be practical. The other thing is to incorporate input from user, being able to accommodate users' preferences in terms of what factors to modify, or what is an ordering of preferences that the person has. Would the person prefer change in carb versus protein versus fat, and so on and so forth. So with that in mind, so these are some of the examples of decision boundary that we constructed based on real data. Blue and yellow ones show basically these adversarial examples that are examples that are generated based on hyperglycemia and normal kind of samples, and the green kind of samples are actually the actual decision boundary between the two classes. So we refer to blue and yellow ones and quasi-hyperglycemia and quasi-normal glycemia samples, and the green one is basically using a bisection algorithm to construct the decision boundary between the two classes. And these plots actually show the kind of construction of the decision boundary. And so for example, on the left, you see carb, insulin, and pre-meal glucose level, but we have a much higher kind of dimension in our data set. So with that, now we can go ahead and move along different axes. And as you see here, the red dot, this is based on real data, that's a hyperglycemic event. So one way for us to move is basically to pick an instance from the decision boundary. As you see here, the green dot on the left is actually, in fact, the closest one, is the nearest neighbor to the test sample, which was hyperglycemia. And we can also accommodate user preference, what you see as the yellow one here, by taking into account what the person might prefer. And you see some comparison against an existing technique called DICE. So we refer to our approach as glycoach. So DICE is a well-known counterfactual explanation technique that has been used in other domains, but as you see, is not as effective in the context here. So examples of the type of recommendations that glycoach can provide. For example, let's look at the second row, which says, okay, the patient prepares a meal, the amount of carb is 74, the amount of fat is 6.4, then the fiber is 3, and the person takes certain 3 units of bolus 5 minutes ago, and their glucose level is 7.2. So now with that, can we prevent this potential hyperglycemic event? Yes, by taking into account the preference of the user, so the patient can basically maintain a normal glycemic response by reducing the amount of carb to 21.3 grams from 74.2. So that's an example of how the algorithm generates certain kind of recommendations, which we need to translate it potentially to more tangible and more meaningful kind of feedback to the user, but that's kind of pure output of the algorithm. Another example, if you look at for example, the last row, that's again, certain values in terms of the amount of carb, the glucose level, when the person took medication, and if they did exercise, some other activities, and they're going to be experiencing hyperglycemia, And the algorithm suggests that you can avoid hyperglycemia by waiting, basically, until your blood glucose level reaches 4.3 from 7.5. So that's another example of recommendation that the algorithm generates. But the bigger question would be, how do we validate these recommendations? So ideally, you want to conduct a clinical trial and test these. But what we can do before reaching that point is, number one, can we test the accuracy? Now, this recommendation that the algorithm makes, does this actually classifies as normal glycemic if we feed it to an external kind of algorithm that predicts glucose response, right? Pretty much like the algorithm that we talked about in terms of hyperglycemic prediction, right? So we can potentially have a model that predicts hyperglycemia and feed these counterfactual examples to that model and see the response. So as you see here, GlutCoach gives us an accuracy or sensitivity of 82% on one data set, 90% on another data set, better than DICE, which is a competing algorithm, and baseline. Baseline is essentially the case where there is a test example that is hyperglycemia, but the counterfactual to that data point is the closest data point from the training data set, the closest normal data point. Basically, it just picks one example from the data set, the training data set. DICE is a method based on mixed integer optimization, and it uses gradient descent to solve the optimization problem. So sensitivity, as we said, that's basically how correctly you achieve normal glycemia. So the accuracy ranges from 82 to 90% on our case. Distance is also one measure that people in counterfactual explanations research people report, which is basically a measure of similarity of the counterfactual explanations and the training data. How close is this to the training data? How representative is? So as you see here in these two data sets, on one we do much better than two others, on Ohio data set. So the distance is 0.33, and the other one, baseline is doing better, mainly because baseline picks one data point from training data set. So we also report PV, which is preference violation penalty. That's the term that we came up with here. Essentially what it means is that, are we taking into account preference of the user? As you see, we're doing better than DICE and baseline on Ohio data set, but DICE is doing better job and nutrition absorption data set. And coverage is another thing. Basically, coverage means percentage of counterfactuals that fall within the feature range of the training data. So we're doing good in there as well. So these are some of the things we can do in order to validate the performance of our approach in terms of hyperglycemia prevention. So the last type of technology I want to very briefly touch on is, how do we design technology that helps with healthy eating recommendations? So what we designed so far is basically predicting hyperglycemia, mostly postprandial hyperglycemia, and try to prevent that. But how can we help individuals in general eat healthy food that is recommended based on their preference, based on what they like, but it also allows them to achieve their diet goal. So assume a person wants to reach from certain calorie level or let's say fasting glucose level, right, to a different goal, right? From left all the way to the right, as you see in this figure, the person might want to lose weight, might want to reduce the daily calorie consumption. So we design an algorithm, a sequential decision-making algorithm, where it provides regular diet recommendation, for example, daily recommendation. And it looks at the outcome, whether this improved the person's dietary intake. And based on that, adjust the recommendation for next cycle and so on and so forth. So it ensures that it makes recommendations to basically such that you were making a minimum amount of change needed, minimum amount of change in a person's diet, but the absolute minimum amount is to make no change, obviously, but with that we won't achieve our goal. So therefore the algorithm is constrained to achieve a predefined calorie goal within a fixed time frame. Depending on how far to the future we want to reach our goal, so we adjust the amount of change in diet. And this suggests eating options based on the user's preference and what they like to eat. So we model this as a linear optimization problem, as you see here, the mathematical representation. Essentially what it means is, if you look at cycle I-1 and cycle I, so we're trying to minimize the amount of change in a person's food, right? P sub ij means the amount of food j at intervention cycle I, right? So you try to minimize it from cycle I to I-1 or from I-1 to I. So you try to minimize, but at the same time you want to make sure there is a minimum amount of change in a person's diet, as you see in constraint number 2, and basically with these constraints. So we solve this as an optimization problem. And I'm going to skip some of the details of that, but here you see an example of the pure kind of outcome of the algorithm. The algorithm, for example, here is said on day 7, these are the type of food that I recommend you to eat. And based on this, the energy consumption will be 2480, protein consumption and fiber consumption are also done. So you can incorporate all these, calorie goal, protein goal, sugar, fiber, all of that into the optimization problem. Another thing is, this is one way to validate it. We collected data with 10 participants over the course of 1 week to 1 month. And then we looked at what they consume, and we used this as a way to simulate interventions for this study. Here you see data from subject 3 and a 3-week-long study. The person has been consuming 3650 kilocalorie per day. They want to reduce that to 2200, for example. And there is, protein goal and sugar goal as well. So let's assume in a hypothetical scenario, so you want to achieve this goal in 7 days. The algorithm realizes that there has to be drastic changes in the behavior, specific in the diet. So therefore, the algorithm would adjust it to certain values to achieve the goal and make the recommendation. As you see in the graph on the right, so that shows the trajectory of calorie reduction over different days, and the person will achieve the goal in 9 days. Of course, this needs to be validated again in clinical trial, and we need to integrate the input from clinicians and patients in order to see how how we can deliver the type of feedback that the algorithm generates. So in summary, so we showed that machine learning algorithms can be designed to predict abnormal glucose levels. And it's possible to use counterfactual explanations as a means to prevent abnormal glucose excursions. We talked about that in the second part of the talk, and we showed that AI methods such as optimization techniques, linear optimization, even reinforcement learning, may be used to provide personalized healthy eating recommendations. So future work and this research will involve integrating additional parameters such as physical activity behavior for intervention design. We need to conduct user-centered design for intervention delivery, how we want to provide feedback in terms of the algorithm outcome, and validating these algorithms, of course, in clinical studies. So I would like to thank our collaborators for these few projects that you saw, Dr. Carol Johnson, Dr. Babak Murtazavi, PhD students Asiful Arifin and Samantha Fessler, and also my former PhD student Nilu Jaribi, who is currently at Microsoft. So Thank you very much for listening to this talk. Please reach out to us if you have any questions or recommendations in terms of how this work can be improved. Thank you.